So my name is Emery Berger, and this is really loud. I'll try to keep it quieter. Is this okay? All right, great. So I'm a professor at the University of Massachusetts Amherst. This is joint work with my two of my PhD students, Sam Stern and Juan Altmaier Pizorno at UMass. Okay. Click. This would be great if this worked. Yes, fantastic. All right, so hopefully everybody in this room is familiar with this family, The Simpsons, right? So it's 2022. But The Simpsons have been on the air for a very, very, very long time. This is what they looked like in the 80s. They looked very different, right? It was a pretty scruffy, not so well-developed family. And I would like this a little lower. Give me 2 seconds. Okay. So likewise, computers have really changed, right? So today you can get an iPhone that's 3 gigahertz with 5 cores, 64-bit processor, 6 gigs of RAM, sits in your pocket. But in the 80s, this is the kind of computer you had, right? So back when The Simpsons first came on the air, you had a 4 megahertz processor, not gigahertz, megahertz, 16 bits, and 640K of RAM, which, as we all know, was enough for anyone, right? All right, so being that computers were so underpowered in the 80s, this meant that really, this is true all the way up through the 80s, that you had to build programming languages that were very close to the metal. So I like to call these metal languages. So the first metal language is assembly, of course. And that dates to 1949. And then you had Fortran, the first optimizing compiler, right? So it was even beyond your ability to program optimizations, right? It would do all this great work. Eventually, we end up with C, and then the meanest of all, C++. All right, so we had these metal languages, and this is what people programmed in because performance was so critical, right? So computers were really slow. You had to squeeze every possible ounce of performance out. And then, as you all may be aware, we went on a 40-year performance ride. So what happened was we went on this ride. Some people refer to this as Moore's Law. I'll talk about it more in a second. But briefly, transistors, that is feature sizes on chips, just started getting smaller and smaller and smaller. And you could just clock up the processors as the signal propagation length decreased. And so this meant that literally every year or two, you could buy new hardware and all your programs would run twice as fast. So optimization was really not necessary. It just required a little patience, and you'd have a faster computer. And so people were like, oh my God, this is going to go on forever. This is fantastic. We don't even need to care about these metal languages anymore. Let's build programming languages that I like to call the irrational exuberance languages, that assumed that performance was going to go up and up and up to the moon, right, forever. So this includes languages like TickleTK, R, PHP, Ruby, and the subject of our talk today, Python, right? So Python, it looks like it's the most advanced in this evolutionary lineup, but Homer's not really the pinnacle of evolution. Is a little plump, not a very lean, mean fighting machine, and so this manifests itself in a number of ways. So when you're programming in a metal language like C++ and you want to know how big an int is, it's 4 bytes, let's say. But in Python, that'll be 24 bytes. And you might ask yourself, why would this be the case? Well, it turns out that Python objects are really fat. They contain a lot of information. They contain like the type information. They contain a reference count. They contain a pointer, and so on. So you don't just get a raw metal int. You get a bunch of goo with it, Homer style. All right, and this is true across the board for all sorts of data structures. So if you have a dictionary, a list of ints rather, that's 24 bytes in C++, well, it's 56 bytes in Python. Likewise, a dictionary from int to int is an empty dictionary, I should stress, is 24 bytes in Python. Today, it's 64 bytes in Python compared to 24 in C, so a little less than 3 times as much. This is a huge improvement, by the way, because up until version 3.6, it was 240 bytes, which turns out to be just about the weight of Homer Simpson. All right, so I've talked about how plump Python is, but there's another problem with Python that you all are probably familiar with. When people talk about Python, one of the things they often notice is that it's slow. It's a very slow programming language. And so why is it so slow? It's not just that it's fat, it's also slow. And the reason at heart is because these metal languages are compiled, right? So they produce really, really fast code. And you spend a little time compiling them, but then at the end, the code runs really quickly. However, most of these irrational exuberance languages started out as interpreters and continue to be interpreters, which means they're very slow. And so I want to illustrate a little bit of what's going on under the covers. So here is a little Python function that adds 1 to a variable, to an argument, and returns it. All right, couldn't be simpler. When you run a Python program, it parses your Python program and compiles it to what are called bytecodes. So bytecodes are a machine-independent instruction set. And then it interprets these bytecodes. And it has basically a giant interpreter loop. So I'm not really expecting you to be able to see what's going on here exactly. But you can see it's a lot more than what happens with C code, where it just converts the add into a machine instruction. Right? So the upshot is you get easily 100x more instructions executed when you're running Python code than when you're running C code. And when you combine this with all the other efficiency opportunities that are left on the floor, you can get pretty extreme performance gaps. So if you take a matrix multiply algorithm, the classic 3 loops, and you write it in Python, just translating that to C will speed up the code by 40x. And then if you just do a few very straightforward optimizations, reorganizing the loop so that it's optimal in terms of memory accesses, using parallelism, using SIMD, you eventually end up with a 60,000x performance gap. Right? And so this 60,000x performance gap, this is like raw Python, and on the far right is using the BLAS libraries from Intel or something, which happen to be conveniently packaged into NumPy, which I'll talk about in a minute. All right, so what happened in 2010? In 2010, this ride ended, sadly. So it was a great time. Fun was had by all. But essentially, you can see, there's all these transistors, and they kept going up, and the trend seems to be continuing on the left, right? So the transistor counts are still increasing. This is Moore's law, right? So a lot of people talk about Moore's law as if it's about speed. It is not about speed. It's about the density of transistors and their growth. And it turns out, amazingly, we're still actually on this path. I mean, it's got to stop someday, right? I don't know, at the quantum level or something. But right now it's still happening. But you can see that it totally flattened out on the right. And this phenomenon that used to allow us to clock up these chips is called Dinard scaling. And Dinard scaling is what really ran out of steam. Or it could produce a lot of steam if you put water next to one of these things. Because basically the chips got so dense that it was impossible, once you clock them up above a certain frequency, to dissipate their heat. So it's not really fun if you're, there were all these graphs that they would have in all these academic conferences about how, today it's like having a 110 watt light bulb, and then tomorrow and then the next day it'll be like the surface of the sun, which is a really hot iPhone. Burn a hole right through your pocket. So what does this mean? Well, guess what? We're still stuck with Python. We're more stuck with Python than ever. It has, if you will, a stranglehold on us. It has become the most popular programming language. But computers are no longer getting fast. So what do you do when you have slow code? You find a profiler, right? So here is a profiler. This is a built-in profiler for Python. It's called cprofile. And this is a really typical result from a profiler. I love it. It says that in this particular code, we're spending all of our time in main. Thank you, profiler. Very helpful. So this is not super useful. There have been many, many attempts to come up with more useful profilers for Python. This is just a collection of some from the ecosystem. There are more that are not listed that I'm not going to talk about in this talk. But I want to bring your attention to 2 of them. These are 2 variants of one called Yappy, which is yet another Python profiler. And there are many more that have followed it. So it's quite a common thing to create a new profiler because everybody is dying from performance in Python. Today, I will be talking about a new profiler from our group called Scalene, but it's quite different from the others, as you'll see. All right, so first, this is not like the most obvious thing I would say about profilers, but it's very important that your profiler actually not slow down your program that much. And the reason I say that is because you've got a slow program on your hands, a slow Python program on your hands. And now you're going to profile it. And if that profiler itself slows down that already slow program, you're going to be in a world of hurt, right? So there are some profilers that actually do very well. So 1.0 is the best. This is normalized to running the original Python program. This is for a benchmark from the PyPerformance suite, which is a benchmark suite that they use to tune Python. Right, so there's a few that are pretty good. There's a few that aren't great. I put these in yellow for caution. This includes the built-in C profile. So the slowdowns range here from 2 to 7x. I should add, as you'll see in a minute, some of these slowdowns also translate to massive losses in accuracy. So the profilers will actually give you wrong results, partly because they're slowing everything down in a weird way. It's biased. All right, so clearly you would not want to run a profiler in this yellow zone in production, maybe in the green zone, but the yellow zone probably not, and definitely not the ones in the red zone. All right, so to make this concrete, the one that's almost 40x, imagine if you had a program that took a minute to run, and now it takes 40 minutes. Right, that's pretty painful. So for most people, this is unacceptably high overhead, which is why it's red, but I've saved the very best for last. You have to notice, so I'm going to go back for a second. The top here was 40. Now the top is 275. Okay? And so this is a profiler called Memory Profiler that slows down execution for this benchmark by almost 300x. But we've seen higher slowdowns for this profiler as high as 1,000x. And when I say as high as 1,000x, I mean I killed it after 1,000x. I couldn't wait anymore. I had life to live. All right, so it's important that to note Memory Profiler is it's not like these other profilers. All these other profilers only profile the CPU. Memory Profiler naturally profiles memory, right? So these are two totally separate things. That said, you probably want both, but you only get one. And if you want memory profiling right now using this profiler, it's very painful. So I'm going to turn this into a form that will be easier to see. So I'm going to rotate this and turn it into a table. So you might be asking naturally, like, where does Scalene fit in? And it turns out Scalene imposes maybe 20, 30% overhead on average. Now I'm going to talk a little bit about some details about these profilers. So profilers typically fall into two categories. These are basically CPU profilers, except for Memory Profiler. They profile either by function or by line. So at the function level, right, you see line numbers, but those line numbers just correspond to the very first line in a function, right? And all the information is aggregated over the entire function. So this is fine if you have a lot of little functions, but if you have functions that are pretty big, it's not very useful, right? So if you have a big, long function, like here's a function, and it says, hey, this function took a long time, and this function is 150 lines of code, this is of scant use. Right? It's like, hey, look over there. And you're like, where? There, over there somewhere. There's a function. It's called big ass function. You figure it out. All right? So there are other profilers that operate at the line level, right? And so this can be a lot more useful. It's especially worth noting that in Python, especially if you're using NumPy or scikit or one of these packages, there's a lot of activity that happens on a line of code. Right? In C++, one line of code probably is not spending very much time, but in Python it could be spending an amazing amount of time, right? Like a trained PyTorch model, right? So there's a lot of work that's happening there, but if you have a very large program, it might be a too fine a granularity, right? So do we do function, do we do line? And the answer is why not both, right? So Scalene does both. It is a profiler that handles both function level and line level profiling. Fine. All right. This one is totally crazy. Some profilers require you to decorate the functions that you wish to profile with an @profile decorator, which is it's beyond annoying. So you put in this decorator, you go through the functions and you put them in. But this is weird, right? Because it's like, hey, I will happily profile for you. Why don't you tell me where the functions are that need profiling? And it's like, but I would like you to tell me that. And it says, no, this is just fine. Just put in @profile. So this is it's a pain anyway, just like changing your code, but also it puts the cart before the horse. It's like, well, somehow you already know. Well, what if you don't, right? Then you're like putting @profile. It's like print line debugging, but for performance. All right, so Scalene does not have this issue, but it also supports @profile, but in a different way. If you actually know where you're looking for and you put an @profile, then it'll only profile those things. But by default, it'll profile everything. All right, what else? Threads. So Python has threads, kind of. So most of you, it definitely does have threads. Concurrency is another question. But as you probably know, there's this thing called the global interpreter lock. How many of y'all have heard of the global interpreter lock? OK, excellent. How many of you love the global interpreter lock? One liar raises his hand. So obviously, for CPU level performance, threading is not so great. But nonetheless, there's stuff that you do in threads in Python, like to hide the latency of network connections, for example. And a number of these profilers just fail entirely with threads, which to us was a big surprise. It's like Python has had threads for a very long time, but these profilers don't support them. Fine. There's something even more remarkable, which is that there is a package called multiprocessing. So if you want true parallelism in Python, you can't use threads because of the global interpreter lock. So you have to use processes. So there is a widely used library called multiprocessing that allows you to run parallel processes. And none of these profilers support them, which is like, OK, great. Like if you're trying to get higher performance and now you have a profiler, no profiler will help you once you embark on the really high performance space. So terrific. All right. So these are not, this is great. This is, we're happy that Scalene works with, broader subset of the Python language and ecosystem. But these features are not the most important features. So it turns out that no past profiler does any of the things listed here on this slide except for one, which is that memory profiler also profiles memory. But as I'll describe, we have this situation where we can profile Python versus C time, system time, memory, GPU, memory trends, copy volume, and detect leaks all at once. And I'll talk about how this all works. All right. The key observation about Python that I think anybody who is looking to improve the performance of their Python code needs to understand, or probably already understands, is that Python is so slow. Your job as a Python programmer is to actually program in C. OK? But what I mean is you program using these libraries that are super performant, that are written in C, C++, or in the case of NumPy, Fortran at the end of the day. Not a lie. That's where you're going to get your performance, right? Because you have this enormous performance gap between Python and C. So really, your job is to find all the Python execution or the Python memory and root it out and move everything to these libraries. All right, so I'm going to talk about Scalene. We call it Scalene because it has the word scale and it sounds like lean, but also because it has these three legs. It's a CPU profiler, a memory profiler, and a GPU profiler. So if you take some code and you run Scalene with it, you get a view like this. And I'm going to walk through a little bit of what this report looks like. So first, it does CPU profiling. When you hover with your mouse over these bars, it shows you, percentages and so on, and you can click on the top header and it'll sort everything by CPU or by memory and so on. The breakdown is every time you see a color that is dark, that means it's in Python. And your goal is to make things light, right? Move away from the dark side, OK? So it breaks down all of your execution and says, hey, there's Python time, there's native time. And if you look and you see native code, and you're spending a lot of your time in native code, congratulations. Right? You've done the right thing. What you're trying to do is to move everything out into native land. It also shows memory consumption. Same situation. It's dark if it's Python memory, and it's light if it's not. It presents average per line as well as peak per line, so you can find things that are really consuming a ton of memory. It also graphs memory usage over time, which can illustrate certain patterns that reveal issues that are going on. So if you have something growing and growing or zigzagging and so on, those are useful. There's a global view as well. Everything at the top is a global summary of the same sort of information, including memory usage over time. And we introduce a new metric that we call copy volume. So let me explain what copy volume is. So copy volume is measured in units of megabytes per second. And what it measures is how much copying is going basically across the Python and native boundaries. So if you're using native code, it's really important, once you're native, you stay native for a long time and then come back with a result. But if you inadvertently take a Python data structure and send it to something, or you load something into a Python data structure, or you put it into an array in Python, it will say, oh, you would like this in Python now. And then it will copy out everything into a gigantic Python data structure. And then if you then, in your next iteration, go and try to run native code on it, it's going to then copy it back and write it in. So you'll be spending a lot of this time, and it's totally invisible. Right? You can't see that it's happening in the source code, and Scalene is the first profiler to reveal that this is happening. And if you spot it, you want this to stop. So this is indicative of a problem. Finally, there's GPU profiling. In this case, we didn't use the GPU. If you have a GPU, it'll show, with an NVIDIA GPU, it'll show utilization and peak memory. All right, so let's dig in a little bit and optimize this piece of code. This is some actual code that somebody sent us where they're like, I don't understand why Scalene is reporting this, this information. And we're like, no, 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 it's doing the right thing. Here's what the issue is. So you can see on the left a bunch of performance, like a bunch of the time is spent in native code. And I already told you, native code good, right? So that seems fine. Here you can see there's 2 gigs allocated in native code. Again, native memory is compact, right? That's the metal representation, super. There's a lot of memory activity, and there's this weird sawtooth pattern. It's a little hard to see, but it's allocating memory, freeing memory, allocating memory, freeing memory. That seems weird, right? That's not something you would expect. And most crucial of all is there's a ton of copying. There's 250 megabytes per second of copying. And basically, once you see this copying and this extra allocation, and you look a little closer at this line of code, it's running some NumPy, and it uses this np.array operator. So np.array converts its argument into a NumPy array. So if you had a Python array, it would then turn it into a proper, like array of floats or array of doubles, right? But it turns out that this thing already generates a NumPy array. And so what does np.array do? You might think it just casts it, but you would be wrong. Because NumPy, np.array, by default, is like, whatever you give me, I will surely convert it to a NumPy array. Is it already a NumPy array? Great, here's another one. All right, so that's the allocation sawtooth explanation. It's allocating a new copy, copying the old one into the new copy, and throwing away the old copy. And it's doing this a bunch of times, and that's what leads to this sawtooth. So what did we do? Guided by this, this insight that we got from Scalene, we went and we got rid of the np.array. So we just deleted a few characters. And you can see that what happens, it's a little hard to see on the screen, but the runtime dropped from 30 seconds to 23 seconds, and the sawtooth pattern went away, and the copying went away, and the peak memory consumption also dropped. Right? So this is obviously a very small example, but you can see, I hope, how this kind of presentation of this information can be useful. Right? You get this holistic view of everything, including this new metric, and this can reveal optimization opportunities. So one of the things we wanted to know, this was not our goal, like we were like, hey, Scalene should be accurate, right? That would be good. It turns out many of the profilers are wildly inaccurate. You would like everything to be along this diagonal. And Scalene is just above it, together with 2 other profilers. The worst you could possibly be is higher, like way high above. If it was going from essentially the y-axis and then over on the x-axis, that's the worst possible situation. And one of the profilers practically approaches it. The upshot of this is, if you use a profiler that's this inaccurate, it will actually tell you, hey, your program is spending a lot of time here. You can go optimize it, but it's wrong. Right? And then you'll optimize it, you'll waste that time optimizing, and then your code will still be slow, and the profiler will not have given you any useful assistance at all. All right? So I also mentioned, obviously, execution time. So Scalene actually has 2 modes it operates in. If you only want to do CPU and GPU profiling, it's somewhat faster than doing the full memory and copy volume profiling. So if you do that, it runs at essentially no overhead. It's like 1x. Here in this talk, I'm just going to talk about with memory consumption, the memory analysis. Memory profiler, like I mentioned, can be easily 200x slower on this benchmark. But Scalene is also profiling memory, and it's like 1.2x. So what's going on? Like, how is it that we're able to do this? So let me first tell you what memory profiler does. Memory profiler tracks every single malloc and free. Python occasionally allocates memory. Right? Like all the time. It's constantly allocating new objects and tearing them down. It has a custom allocator designed to make this fast, but when you impose tracking on every single one of those, it's very, very costly. So every single time there's an allocation, memory profiler records malloc info, right? Malloc info, it records the free info, records malloc info, and so on. And you can easily see how this can be very, very expensive. So Scalene actually adopts a new sampling strategy where it's essentially a kind of threshold-based sampling. So it only tracks every time the delta of memory consumption, so whatever your high water mark is, or your current high water mark, is as soon as it's, if it's like going up and down, and it's not crossing a megabyte threshold, there's no recording. So let me illustrate this with some Maggies. So during this whole regime, there's nothing that happens. You're just allocating and freeing and allocating and freeing, kind of part of what Python is just doing on its own anyway. You don't care if it's at a stable point, right? If it's not really consuming a ton of memory. But once it crosses that megabyte threshold, it records the malloc info. And then it waits until it goes up or down by another megabyte. And then when it does, it'll record malloc information again. So unlike most sampling approaches, this is actually precise. Like whenever you go up and up and up, you will catch all of that memory consumption. If you ever allocate a very large object, it will definitely, like if it's more than a megabyte, you're definitely going to record it. But most of the time, it's like a low-pass filter. It just filters out a lot of the allocation activity. And this gives us high accuracy with very little overhead. All right? So that's how we get very granular memory information with Scalene with low overhead. Let me talk a little bit about our jujitsu hack that allows us to get to break down CPU time by Python time and native time and also system time. So there's a thing that all interpreted scripting languages from the 90s, all the irrational exuberance languages do, which is called deferred signal delivery. So what does this mean? So it means that when there's a signal, like a timer signal, which is a thing that profilers rely on, right? They go tick, 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 and they send a signal. Python actually hijacks all of these signals, right? So the signal is actually always caught by Python and then delivered. It's a pretend version of the signal in effect. Perl actually does this now. It used to not do it, and it would periodically break the interpreter. There are very good reasons for doing this deferred signal delivery, but it has some negative effects. So suppose you write a profiler, and you would like regular timing interrupts, right? So every 100 milliseconds. So if you're running Python code, basically these are delivered promptly. As it's interpreting bytecode, in effect, every so many bytecodes, it's going to actually check and say, oh, are there any pending signals, and it'll deliver them. So as long as you're running pure Python, this is fine. However, if you're running native code, the whole time you are running a function call into native code, all signals are deferred until you finally come back to Python. All right? So if you were saying, hey, I want to see how much time I spent running this code, the whole time it's executing native code, it's effectively comatose. All right? So, you know, the C, like, it's like I could spend a year running C code, and then I'll come back, and it'll be like, oh, only 1 second has elapsed. All right? So this is not exactly ideal. It makes it challenging to write a CPU profiler. But it turns out that we can actually leverage this. So we're going to turn lemons into lemonade. So what we're going to do is every single time we take one of these signal interrupts, we're actually going to record the time. So we're going to record the process time or the virtual time. And every time we come back, we're also going to record the time. And then we're going to compare them, right? And so we're going to observe if we were delayed. Why did we get delayed? Well, it's process time. The only way we could be delayed is because we were running code, right? Native code. And so what we can do is actually straightforwardly say, every time we get one of these interrupts, we accrue whatever the expected interval was to Python time, and then we add delay minus interval, which is the waiting time, to native time. All right? It's a very simple equation. It actually, we have a formal proof that this works. So it actually does what it's supposed to do. So you can take this to the bank. All right, so finally, I want to talk a little bit about automatic memory leak detection. So memory leaks are an issue in Python, despite the fact that it is a garbage collected language. And people, I think, some people think erroneously that garbage collection prevents memory leaks. It does not, because if you have a pointer into any object, and that object, you forget about it, well, that object can never be reclaimed. So that can lead to a memory leak, but it gets worse. You're now using C code, and the C code can also leak, and you can have cross-language leaks. So it's a very messy situation. You can have C code that's tying down a Python object. All right? So even a Python-based leak detector won't be able to find what's going on because it's actually, the pointer is being held in C state that it doesn't examine. It can't. So it seems like a hard problem. We solve this problem in a kind of roundabout way. It involves donuts. So this is a talk like Simpsons inspired, so donuts had to appear. So for every malloc, we say malloc instantiates a new donut, all right, at that line. And every time there's a free, Homer eats that donut. All right? Now you can see that if you are in a steady state, nice situation where whenever the donuts appear, Homer eats them, right, we don't have a leak. All right? So we're literally going to keep track of, in some way, on a per line basis, the rate at which donuts are being created and the rate at which they're being consumed. And if we discover, hey, there's a bunch of donuts, but there's not matching homers, we have a memory leak. All right, so we could do this by tracking every memory allocation and every free, but I've already shown you that for Memory Profiler, that's a disaster, right? It slows things down massively, and we did not want to do that. So what we do instead is we do a kind of random sampling. So we periodically randomly choose allocations that we're going to track, and we say, oh, you allocated this donut. What is its address? And then we go and we check just when we invoke free, hey, was it this address? This is a very cheap check, right? It's literally just a comparison. The comparison is generally false, so it's well predicted. And if it detects that there's a matching free for the donut, right, then it says, great, I'm going to increment a count. Right? So what we do is, in effect, we start out with everything getting one donut and one homer. This is required so we don't do division by 0. All right? And then we observe for all the lines over time what's happening with the donuts and the homers. So we count up the donuts and the homers and we compare them. And if we observe a large enough number of donuts and not enough homers, we apply this thing called Laplace's rule of succession to conclude that this is in fact a memory leak. All right? And so when this happens, it actually reports leak volume per line. So let me show you what this looks like in the UI. Here you can see underneath the little memory timeline thing, it says in red, possible leak. And you can see that the memory activity is going up, which could be legit, but here it's like, this looks like a possible leak. And if you mouse over it, it says there's basically the probability has to cross some threshold, like 99%, and it'll report this. And it says, here's the rate of leaking. So it's leaking 0.3 megabytes per second. So why is this useful? So obviously it's useful to track down memory leaks, right? Memory leaks are bad. But it's also useful because we measure how severe the memory leak is. Not all memory leaks are created equal. And if you have a memory leak where it's like, well, this is only going to run for an hour, and it's 0.1 megabytes per second or something, do the math, OK, we'll be fine. We're not going to consume too much memory. But if it's 20 megabytes per second, you're probably doomed. Right? So this gives you a way of prioritizing this just by looking at the rate of memory leaking and deciding what you're going to do with it. All right, so I'm going to conclude. Scalene is this new profiler for Python that does a bunch of things: CPU profiling, memory profiling, copy profiling, and GPU profiling. Unlike all past profilers, it also, well, it works for a bunch of Python code that the other past profilers don't work on, but it also reports the breakdown between native code and Python code, native memory and Python memory, and this is very useful, we believe, in getting decent performance out of Python. You can easily install it using pip or conda. That was a journey, getting it to work with conda, but anyway, there's a like 80 commit message chain of me discussing with the conda people, like what now? But anyway, it's been downloaded about 370,000 times to date, which is nice. You can go get it on pip, but the GitHub site that is there below is also in the QR code, has the information and how to use it and other documentation. And in sum, we want to get out from the stranglehold of Python, but we still want to use Python, but we want it to be fast. And so hopefully Scalene will help us on that journey. And thanks for your attention. Right, OK, great question. So the question is, I mentioned that there's this sort of 1 megabyte threshold for the sampling for memory profiling. Can you change this? And if not, or even if so, why did you choose 1 megabyte? So it's actually closer to 1.5 megabytes, and it's actually a prime number for reasons, mostly having to do with stride. So if you're always allocating the same amount of memory, it could end up triggering it all the time and not breaking it up in a kind of random way. It is currently not configurable, but we have thought about making it configurable. But we're not going to put in the complexity unless people are like, please, please, we really need it to be configurable. There's an obvious trade-off between the amount of memory that's consumed, or the amount of memory that's sampled, and then the accuracy. And we felt that something that's close to a megabyte in granularity would be intuitive for people, that people like to think about things in terms of megabytes. But of course, in your world, it might be gigabytes. And then maybe 1 megabyte granularity is too fine. But that's the reason we chose that number. So great question. Yeah, multiprocessing. So the question is, well, tell me about multiprocessing, and I guess the hidden question here is why? Why is it we're the only profiler to do it? It is not rocket science, what we had to do. We had to insert ourselves in every process that got launched so that we were tracking it. So we did this basically by hijacking exec. And because you can do all these crazy things in Python, we did. So we did that. So we track all these spawn processes, and then they record all this information, all the profiles in temp files with PIDs attached, and then we aggregate them. So again, it's not rocket science. It's just that I think people either didn't know that they should profile it, or they didn't really think. They didn't think to try. I'm not really sure, but in any event, we were like multiprocessing, clearly important. We should make that work, and that was all done by my student Sam. Are there practical tips? This is the question, I think, right? Are practical tips or hints or pro tips for not screwing up performance with Python? Yeah. So loops are bad. Okay. That sounds really simple. You know what else is bad? Comprehensions. So list comprehensions, also bad. Those are just loops. They're expensive loops. Anytime you're spending a lot of time in Python and you're doing iterations or you're doing this generation in Python, that's going to kill you. And so for NumPy, the trick is to always do vectorized operations. You do these broadcast operation stuff. That all happens in C land. So you want to keep as much of the C stuff happening in C land. And loops are almost always a bad sign. That's an anti-pattern. Great question. Yes? So the question is, hey, you're writing Python code, but you're not writing Python code. I view this as sort of a Fight Club thing, right? Like it's like first rule of Python Fight Club is there is no Python Fight Club, right? So you're not supposed to program in Python to the extent possible, but that's overstating the case, right? The fact is that there's like every library under the sun has Python bindings, like all of them. Right? And maybe some of them have Java bindings and some of them have other bindings, but boy, they all have Python bindings. And so if you want to get shit done, I'm being recorded, oh well, then Python is the way to do it, but you also want to be careful. And the problem is it's very easy to get bitten by these performance issues because you're just like writing and connecting things up and you write in a kind of reasonable way that may or may not be good enough. And for prototyping, it's fantastic. But I can tell you that when you actually turn this into real code, so this is we have an issue for success stories that was inspired by Julia Evans, where we just ask people to post their success stories. And so this was from somebody at Semantic Scholar, and these are sophisticated people, but they're doing a bunch of machine learning. I mean, and they're doing a bunch of machine learning, and of course they're using these machine learning libraries, but they needed to be able to find out what was going on and what was taking their time, and they basically were able to get their costs down by 92%, which is, to me, insane. But there's so much low-hanging fruit in Python because it is so slow. So if you can root out all the Python stuff, you can really have a big impact. It's a lot better, like when I talk with folks in native land in C++, right? You're like, yes, we got a 5% performance improvement. 5%. Right? It's in Python, you get rid of some Python, you get 5x performance improvement. I have a student who reported that improving their NumPy code, they got a 20x improvement, right? Driven by Scalene saying, oh, hey, this is what you really should be looking at. So I'm in violent agreement with you is really what I'm saying. All right, thanks very much for your attention. I'm happy to talk after.